Hello, and welcome to your naive Bayes and k-nearest neighbors lecture. Now, today we're covering two different algorithms, but that's because these are two of the most conceptually simple machine learning algorithms we're going to learn in this class. First, let's start with naive Bayes. One thing I really like about naive Bayes is that the two most important things to know about the algorithm come from the name, the fact that the algorithm is naive and the fact that the algorithm is Bayes. We'll start with the Bayes part. The Bayes in the naive Bayes name refers to Bayes' theorem. Bayes' theorem is just a formula for calculating a conditional probability. For instance, if you want to know what the probability of A is, given that you already know B, you can calculate that by using the probability of B given A times the probability of A divided by the probability of B. One way to interpret Bayes' theorem is to say that we're taking the overall probability of event A and we're updating it based on the fact that we know event B happened. The way we're doing that is we're taking that probability of event A and we're multiplying it by these values. And this basically helps us update that probability by saying, now that we know that B happened, how do we change the probability that A has happened? The way we use this in the naive Bayes algorithm is to use Bayes' theorem in order to calculate the probability of someone belonging to a specific category, given the observed predictors. The way we do that is we just plug these two things into Bayes' theorem. So the predicted probability that you're in a category, given the different values of your specific predictors, is equal to the probability of seeing your specific values of the predictors, given that you're in that category, times the overall probability of being in that category divided by the probability of seeing those predictor values. Let's look at a specific example. Here we want to predict whether or not someone had a heart attack based on whether they're a smoker, whether they're diabetic, and whether they're obese. Then we can compare those two probabilities. The probability that someone has a heart attack given that they're a smoker, they're diabetic, and they're obese, and the probability of not having a heart attack given that they're a smoker, a diabetic, or obese. Whichever one of these categories has the higher probability is the category we'll classify our data point as. For both of these, the way that we calculate this is we say, well, if we know that you had a heart attack, what is the probability that you're a smoker, you're diabetic, and you're obese? Then we take that and multiply by the overall probability of having a heart attack. Luckily, most people don't have heart attacks, and so we want to make sure that we take that into account. Then we divide by the probability of seeing someone who is a smoker, who's diabetic, and who's obese, just overall. Then we repeat that same process, but with the category no heart attack. Now, one thing you might have noticed about our formulas is that they have the exact same denominator. And since our goal is just to compare the two values, one thing that we can do is just toss those denominators right out. It saves us some computational power because we don't have to calculate them anymore. And because both are divided by the same value, the one that's bigger is still going to be bigger because probabilities can't be negative. Now, because we're getting rid of this denominator, the thing that we're calculating is not technically a probability, it's proportional to a probability. In math notation, this little squiggly guy basically means proportional to. While we're not calculating the exact probability anymore, we're calculating a score that's proportional to the probability, meaning that whichever category has the higher score is still the category that's most likely. So once we have these two scores, we look at them, and whatever category has the highest score is the category we classify our data point as. So that's the Bayes part. Now let's talk about the naive part. The naive part of the naive Bayes name refers to the fact that our algorithm makes an assumption we know is false, and yet it still makes that assumption. This assumption has to do with the probabilities that we're calculating. As you saw before, one of the things that we might need to calculate, for instance, is the probability that someone is a smoker, diabetic, and obese. Now, in the real world, we know that these three things are related. For instance, if you have a chronically high-stress job, you might be more likely to smoke and also more likely to be obese because you don't have access to simple, easy meals that you can cook at home. So we know these two things are related. And because they're related, the way that we calculate this probability of being a smoker, being diabetic, and being obese is using this formula. First, we take the probability of a smoker given that you're diabetic and obese. Then we multiply it by the probability that you're a diabetic given that you're obese. And finally, times the probability that you're obese. And that ends up being a lot of different conditional probabilities that we have to calculate. But what if we make the incorrect assumption that all of our predictors are independent? Well, then our calculation is a lot easier. If we assume that our predictors are independent, so for instance, being diabetic has no relationship with being a smoker, then what we can do is we can just take the probability of each of our individual predictors and multiply them together. No calculating these complicated conditional probabilities. But we know that this is false. In the real world, our predictors tend to be related. They're not independent. And yet we're going to make the assumption that they are and calculate our probabilities as if they're independent. Thus, that's pretty naive. Now, technically, naive Bayes assumes something called conditional independence. This means that we're not assuming that being a smoker, being diabetic, and being obese are independent in general, but within a given category, so within people who've had heart attacks, we're assuming that they're independent, or within the people who haven't had heart attacks, we assume they're independent. Now, just to clarify some of this terminology, let's look at what it means for two variables to be independent. Here I have a very small data set that looks at whether or not someone has taken CPSC 392 and whether or not they're a business major. We want to check if these two things, being a business major and taking 392, are independent. The way that we check that is we look at the probability of taking 392 and we see if it's different than the probability of taking 392 given that you're a business major. If these two things are independent, then that means that knowing someone's a business major gives you no information about whether or not they've taken 392. If they're not independent, then knowing someone's a business major might improve your ability to predict whether or not they've taken 392. First, let's look in our data set what the probability is of taking 392. Well, there's 20 total students in this data set, and of them, 10 have taken 392. So the probability of taking 392 overall is 0.5. Now let's look at the probability of taking 392 given that you're a business major. This means that we're only going to look at rows of people who are business majors. In other words, these rows right here. In this data set, there are 9 business majors, and of them, 6 have taken 392. This means that the probability of taking 392 given that you're a business major is about 0.67. Notice there's a big difference between the overall probability of taking 392 and the probability of taking it given that you're a business major. This means that knowing someone's a business major helps you improve your prediction of whether or not they are going to take 392. Thus, these two things are not independent. Knowing someone's a business major gives you information about whether or not they've taken 392. So let's look at a really quick example of using the naive Bayes algorithm. Remember, our goal is to calculate the probability of a category given the different predictors that we have. And the way we're going to do that is by seeing how likely is it that we would see these predictors given that we're in a specific category times the probability of being in that category. One really classic example of the naive Bayes algorithm is using it to classify emails as either spam or ham, real emails. Here we have a data set that gives us 4 different predictors: whether or not the email has the word Viagra, whether it has the word love, whether it has the word dollar, or whether it has the word buy. Let's say that you're looking at an email that says, "Hey Chelsea, I would love to buy you lunch, call me back." That email does not have the word Viagra. It does have the word love. It does not have the word dollar, and it does have the word buy. So let's use those features to predict whether or not this email is a spam email. First, we need to calculate this part. This is saying, given each of our categories, what is the probability of seeing an email like this one that does not say Viagra, says love, does not say dollar, and says buy? Let's look at the ham case first. So for a ham email, what is the likelihood of seeing an email like this? Well, the probability of seeing the word Viagra is 0.03. So the probability of not seeing the word Viagra would be 1 minus 0.03. Then we're going to multiply that by the probability of seeing the word love, because the word love appeared in my email. That probability is going to be 0.36. So I'm going to multiply by 0.36. Now, my email did not say the word dollar. In a ham email, the probability of an email saying the word dollar is 0.02. So the probability of not would be 1 minus 0.02. And finally, my email did have the word buy. The probability of seeing that in a ham email is 0.02, so I'm going to multiply by 0.02. Remember, the reason we're able to just multiply is because we're assuming that these predictors are independent. This part that we just calculated is this part, the probability of seeing these predictors given we're in the category ham. Now, the last thing we need to do is multiply by the probability of being in that category. In order to do that, we'll just multiply by 0.5 because in this data set, 50% of the emails are ham and 50% are spam. When we multiply all that together, we get about 0.0034. That's our score for a ham email. Now we need to calculate our score for a spam email. Again, the first thing we need to start with is this part, the probability of seeing our data given our category. For a spam email, the probability of seeing the word Viagra is 0.32. So the probability of not seeing it is 1 minus 0.32. Then we look at the probability of seeing the word love because our email saw the word love. In a spam email, that probability is 0.05. Then we multiply by the probability of not seeing the word dollar. In a spam email, this would be 1 minus 0.83. Then we multiply by the probability of seeing the word buy. In a spam email, this is 0.74. Now again, we've calculated this first part, the probability of seeing these different predictor values given that our email is a spam email. So we now need to multiply by the probability of seeing a spam email. In this data set, it's easy. It's 0.5 because I've told you that half the emails in this data set are spam. When we put that all together, we get about 0.0021. Now remember, these two scores are not probabilities, but they're proportional to probabilities. So all we have to do is look at which score is higher and choose that category. In this case, that would be ham. Since our score for ham is higher, we are going to classify this email as a ham email. What we've been doing so far is something called Bernoulli naive Bayes. Bernoulli refers to the fact that all of our predictors were binary. They either had a 0 or a 1. The Bernoulli part just tells us how the model is getting the different probabilities we're using to calculate that naive Bayes score. However, we can also have models that use categorical variables that have more than 2 categories. We, in this case, would use categorical naive Bayes. The categorical refers to, again, how we're calculating the different probabilities that we'll use to calculate that score. And our predictors don't just have to be categorical, they could also be continuous. For instance, if we use continuous predictors, we would use Gaussian naive Bayes. Gaussian refers to the effect that we use a Gaussian or a normal distribution in order to calculate our scores. And that's literally it. Remember, the two important things are that naive Bayes is naive and it's Bayes. It's naive because we make an assumption of conditional independence. Within our different categories, we assume that the predictors are independent. Now, we know that's not true, so it's a naive assumption to make, but it makes the calculations a lot simpler because we don't have to calculate all those conditional probabilities. Naive Bayes is Bayes because it uses Bayes' theorem in order to calculate scores that we can then compare. Whichever category has the highest score is the category we choose to classify our data point as. Now, we're not using all of Bayes' theorem. Remember, we throw away the denominator, so that can make our computation a little bit easier as well. All right, on to k-nearest neighbors, or KNN for short. K-nearest neighbors is a classification algorithm that basically operates on the idea that birds of a feather flock together. This means the data points that are similar to you in the predictors are going to likely be the same category as you. For instance, let's take this data and say that we're trying to classify a data point that's right here. Well, k-nearest neighbor says look at its k nearest neighbors and classify this data point as whatever category is most common among those neighbors. K is just a variable that we get to choose. So for instance, let's look at k equals 3. For this data point, its 3 nearest neighbors are this, and this. When we look at these data points, we can see that 2 out of the 3 are in the gold category and 1 is in the blue category. So we would classify this new data point as gold. And again, K is just a variable. We could look at 1 neighbor, 10, 20, 100. This is an example of something called a decision boundary. Now, decision boundaries are mostly useful when you only have 2 predictors, which is almost never, but it can give you an idea of how the algorithm is making a decision. You can make decision boundaries for any of the different classification models that we've used. Here I've used it for K and N. Basically what this decision boundary tells you is if I had a data point that was in any of these regions that are covered blue in the background, we would classify this data point as blue because its K nearest neighbors, most of them are blue. Anywhere in this region would be classified as gold because most of its neighbors are gold. And that's literally it. In K and N, all we have to do is choose K, and then for every new data point we want to classify, look for the K nearest points in our training data to this new point, and whatever the majority class is, classify our new data point as that class. What's a little more difficult is choosing that value of K. Now, one way you could choose that value is you could have some sort of domain expertise that gives you intuition for what K should be. For instance, if you're looking at baseball data, maybe you want to look at the 40 nearest points because you think that the 40 nearest points are all going to be players that are playing the same position. And this is based on your knowledge about baseball. But in almost every situation where you're using K and N, you're not going to know what that value of K should be. So instead of using your domain expertise, what you can do is use something called hyperparameter tuning. Hyperparameters in a model are parameters that change the behavior of the model, but aren't selected by the model. For instance, in something like a linear or a logistic regression, our coefficients were examples of parameters. These are values in our model that the model chooses. Hyperparameters like K are things the model needs to know, but it doesn't choose. We as the people building the model need to choose that value. And we just talked about the fact that if we have some type of expertise in the data that we're working with, we might be able to select a really good value. However, most of the time we won't be able to. So we might want to use the data to decide. But how would we do that? Well, one option would be to fit a model with K equals 1, and then 2, and then 3, and then 4, and so on, and then see how those different models perform on unseen data. Whatever model does the best on unseen data, we'll choose that hyperparameter. So if our model with K equals 3 does the best, we'll choose K equals 3. But we have a little bit of a problem. Remember when we first talked about training and testing data? We said that the test set is supposed to be pretend future data, data that has never been seen before. But if we use that data to choose our hyperparameter like K and K and N, then we've looked at our data. It has informed the structure of our model, and therefore it's not truly unseen data. Remember, what we should be doing with a train test split is training our model with some pre-specified K value and then testing it to see how well that model does on unseen data. But we want to use unseen data to choose our hyperparameter, so we must make an additional split. Instead of just having a training and a testing set, we're going to have 3 data sets. The training set, the testing set, but now the validation set. The training and the test set are basically the same as before. Your training set is what you use to actually build your model, and your testing set is what you use to evaluate the model once it's completely built and to see how it does on unseen data. The validation set is essentially a pretend test set. We are going to train a bunch of different models, each with different values for our hyperparameters. And we now want to know how each of these models performs on unseen data, but we can't touch our test set. So what we're going to do is use our validation set. We are going to see how each of these different models perform on the validation set. The one that performs the best is going to be the hyperparameter that we pick. For instance, let's say that we choose K equals 4. Now that the model has been fully built, we can then use our test set to see how that model does on unseen data. Because we used our validation set to choose our hyperparameter, our test set is still unseen. And this can generalize to more than one hyperparameter. For instance, in decision trees, we talked about two different hyperparameters. We talked about max depth, which limits the depth of the deepest part of the tree, and we also talked about min samples leaf, which tells you how many samples a leaf must have in order for it to be split. We can use this hyperparameter tuning to choose any number of hyperparameters that we might need for our model. In KNN, it's just one, but in other models, it might be more. Now, there's many ways to choose what hyperparameters we're going to test out in our model. We're going to only talk about two pretty simple ways. The first one is called grid search. Like the name implies, grid search is basically a brute force way of choosing the hyperparameters that you're going to test, and then of course you're going to test them, see which one performs the best, and use those hyperparameters in your final model. In grid search, for every single hyperparameter that you have, you give it a specific list of values that it should try. It will then try every single possible combination of these values. Whichever combination does the best on the validation set is the combination that you're going to use in your final model. Another option is something called random search. Random search, like grid search, is a way to define what combinations of hyperparameters you're going to test out in order to see which one performs the best. In grid search, what we did is we gave a specific list for each hyperparameter of what values we wanted to try. And then grid search is going to try every single combination of those specific lists. For a random search, instead of giving it a specific list of values that we want to try, we basically give it a range or a distribution of values that we want it to try, and it randomly selects combinations using those ranges or distributions. This graph sort of gives you an intuitive idea of the difference between them. In grid search, we pre-specify the individual values that we would like to try for this hyperparameter, and we try every single possible combination across all of the different hyperparameters. In a random search, we provide a range or distribution of the hyperparameter values, and it will randomly select combinations to try. But in both these cases, what we're doing is defining how we would like to try different hyperparameters, and these take care of defining what combinations we're going to use. We then take all those combinations, build models with them, test them on the validation set, and choose the best one in order to build our final model that will then be tested on the test set. Remember, KNN is really simple. Birds of a feather flock together. The category of a new data point is likely to be the same category of most of the data points around it. However, in KNN, we've now run into this issue of hyperparameters. Hyperparameters are things that the model needs and that changes the performance of the model, but that the model doesn't choose. We must choose it, and sometimes we don't have the domain expertise to do that, so in order to choose them, we might use something like hyperparameter tuning. All right, that's all I have for you. I will see you next time.